Hello. So, welcome. Today we're going to talk about Swift and techniques you can use to integrate Swift into your Kotlin projects and the reasons why you may need to do that, and also going the other way, how to take your Kotlin code and then use that from some Swift project. So I have a lot of slides to cover. There's quite a bit of ground we need to go over. So I'll go pretty fast, but hopefully you can get the idea of what the techniques are and how to do them. So Swift is kind of annoying because it doesn't integrate with Kotlin. Kotlin doesn't support Swift directly. So we have to do a bit of a kludge. We take our Swift and we need to wrap it with an Objective-C API. And if we do that and then build it as a Cocopod, we can then bring that into our project, and then the Kotlin code can see the Objective-C code, which is our API, to the Swift code underneath. And this is a technique we use to access Swift modules that we otherwise wouldn't have access to on the Apple platforms. And going the other way is a little easier. Kotlin native, you just build your Kotlin code, and you vend it as an XC framework in your configuration. And then XC frameworks can be consumed by any Swift code as a standard part of the build process. So it's not quite as simple as that. There's a few curly things to take care of. The compatibility for the Apple system has a few wrinkles, and primarily what we're leveraging is the C compatibility with Kotlin, which is very, very strong. It has really good C support, and Objective-C is just C. So, I mean, famously the first version of Objective-C was the regular C compiler with just some preprocessor macros and some library code. And it just looks exactly like C, it just has a funny syntax and all of that. So C works with Kotlin really, really well. Swift does not. And this is increasingly a problem because there are new modules coming out from Apple and from the Apple community that are written only in Swift. Because Objective-C is pretty old now, it's like the same kind of age as Java. And Swift is now like 8 years down the track. So people are writing mostly to Swift now, and if something's just in Swift, we have no access to it from our Kotlin projects. And so there's key parts of the Apple ecosystem now. If we want to really integrate with these platforms, we need to access those Swift modules, otherwise we can't do what we need to do. Fortunately, the Swift compiler has really good support for Objective-C Swift interop, and we can leverage that to build our API layer on top, and then use that to vend it into our application. And going the other way is much easier. We can just call Kotlin from our Swift code. The type system gets a little bit funky, but mostly it just works. Now, just a small side note, the C compatibility. If you're doing stuff on native on the Apple platforms, the C stuff is really, really powerful, and there's a bunch of stuff in here that's really useful. If you're a C programmer, this is just like normal C, but in Kotlin. So you can do things like just allocate some space on the heap, do something with it, and free it. It reads just like normal C. This is regular C stuff, but we're in the Kotlin world, and that's super powerful. There are two libraries that you should look at if you want to look at some of these things to try and get leverage on these platforms. Platform.darwin and platform.foundation. If you dig around in there, you'll find lots of really interesting stuff. And you can get right into the bowels of the system and do all sorts of crazy things that you otherwise might not have access to. So we're going to leverage Cocoapods to get Swift into our app. And Cocoapods is the Objective-C dependency manager that's been around for a while. And it builds Objective-C frameworks. And Objective-C frameworks we can consume directly from Kotlin as C code. If you go to their homepage, this is the claim they're making on there right now. So there's a really big code base out there. You might find the stuff you need already exists, and you can just pull it in and use it. And I want to go through an example of how to do that. So there's an example pod. AF networking is super popular. And if you go to the homepage for any pod, you'll notice two things on the bottom right. There's a pod spec and a GitHub repository. And that's really all you need to spin up a Cocopod. And we'll do that ourselves to spin up our own in a little bit. But first, let's just bring this example in. A pod spec looks like this. I apologize for the Ruby code. Cocoapods was written in that really short period in history when Ruby was popular. And apologies to any Ruby enthusiasts here. So the whole toolchain is written in Ruby, and the pod spec is then also Ruby. But fortunately, all we need to know is what's in this one little file, and it's pretty easy to just cut and paste an existing one and modify it to what you need. The one thing I wanted to point out, though, is it has the regular things that any packaging system would have. There's a name, there's a version, there's where to get it from, what targets it supports, all the usual type things. Now, to bring this into our project, there's a plugin for Cocoapods that is super easy to use. We essentially writing a DSL here that's almost the same as that pod spec we just looked at. When we write that last line, pod, AF networking, that keys us into the entire Cocoapods ecosystem and says, we want to consume this pod as a dependency and bring it in and use everything from that pod and everything that that pod includes. One word of caution, when you do modify your Cocoapods plugin, there's some stuff going on with caching that tends to be broken a little bit, and it's best just to clean everything and resync your Gradle files, otherwise you won't see the changes. Often it doesn't work properly, but once you do it, it all works really well. There's really good documentation on how to use this plugin, so go there if you need to do that. So let's build a little example. Let's take a sample module, not a real app, but we have this module called module, and we put the Cocopod plugin in there, and when we compile it, it emits these artifacts. We get a pod spec that's generated on the fly, and it just drops that into the root folder of the module. And in the build artifacts, you'll see a module.framework, and that's the actual framework that we include. It gets linked into the project automatically, and you can then use that code. So that pod spec, you can commit that if you want, or you can just let it be generated whenever you run compile. The generated pod spec looks like this, exactly the same as the other one. The one point of difference is it has a dependency now. That dependency is that AF networking, and that one little tag that tells Cocoapods when it runs to go to the GitHub repository, find out where AF networking is, download it, compile it, build it into our system, link it with our library, and then vend that framework. And then to use it is super easy from there. Once we have that building, we can just import cocoapods.af networking, and then all of the symbols under that are available. In this example, we're just using the reachability manager to set a callback. This is fired every time the reachability changes. And you can see we're just in normal Kotlin land at this point. There's no funky stuff. The method names are pretty long because it's Objective-C, but it just feels like normal Kotlin and works like normal Kotlin. And this is the power of the C interface underneath. And just for interest's sake, this is the Objective-C code. There's a reason why people are writing Swift now, because they want to write this. It's really wordy, it's quite verbose, it's pretty weird looking these days. Nobody wants to do it, so everybody's writing Swift. So that's pulling in a remote Cocopod, and you can publish your own Cocoapods to remote. It's a little bit more work. I'm not going to go into that today. I want to talk about just having Cocoapods run directly in your project. And so we have the same project. What we're going to do is add a folder for our Cocoapods. We'll call it Cocoapods, and inside there, all we need to add is the pod spec itself, and we need to write that. And we'll drop our Swift files, and we're going to write a Swift Cocopod directly into this file structure. And there's a reason for the file structure. I'll get into that later. But we set it up like this, and then we all throw our pod spec. And pod spec for this is pretty simple. We're just saying, okay, we just have a version, we have a name, and we give it the folder for the source files and tell it to bring in all those source files. And when we build this, the Cocoapods plugin will run, and it'll compile everything in there and build that framework, just like it did before. And one thing, a warning, there's a use frameworks directive that if you search on the internet for how to write pod specs, you'll find this a lot, and there's a lot of misinformation about what it does and what it's for and everything else. It's completely obsolete. Just avoid it. If you see it, ignore the discussion around it. Don't use it. It's no longer relevant. So pod specs, we can run a pod command to check that our pod spec is valid. And podlint does this, podliblint, and it puts out a lot of warnings, so I often use --allow warnings. And we just do that to validate that we wrote the right pod spec before we go and build everything else, because you'll run into troubles later if it doesn't build cleanly as a standalone pod. So going back to our Cocoapods plugin now, this is what we had before. And we modify it slightly to say, okay, we're no longer pulling in AF networking. We're going to pull in this local pod, which is the same syntax, except we add some extra parameters. We add the version, and we tell the source to point to a local file structure. And that's, in this case, .cocoapods my pod. And once we've done that, we can build it, and it'll generate the pod spec like it did before. This is the synthesized pod spec that it just magics up out of nowhere. And instead of AF networking now, we've got this local mypod, and everything builds great. So to use it, just like before, we can just import cocoapods.mypod, and everything is there, and we can use everything that's in that Cocopod. So we can then write a bunch of code in there and build this, and it's part of our local project, and we can just use it directly in our project. Now there's an extra thing to note in the build artifacts. You'll see some workspaces that are built. These are the normal Cocoapods output. These things you can open in Xcode. So if you do that, you can, if you want to use Xcode, you can. And this project, the folder structure is a little weird. You get pods, and then under pods is development pods, and inside there is your pod, and then the source files are in there. But they all link back to the actual folder structure that's on disk. So if you open it in Xcode and edit this project that's sitting in the build folder, you actually edit the real code. So this can be a useful workflow if you wish to use Xcode. If you don't wish to use Xcode, just don't use Xcode. But it's there if you want to use it. So how do we bring in Swift to this picture? We have to use a technique called bridging. And essentially, we use the compiler to make our Swift look like Obj-C. And mostly we use this at Obj-C annotation to do that, which directs the compiler to say, okay, we want to output Obj-C for this, not Swift. And it does a bunch of stuff to make everything just work most of the time. And then we use the Cocoapods plugin like we normally do, and it builds a framework, and we can build the framework and pull it into our Kotlin project, and away we go. So here's some Swift. It's a really simple class. It has an initializer. It has a single public method that takes a string. And if we build this, even though everything's public, when we build this as a Cocopod, we won't see anything. We'll import Cocoapods, and there won't be anything to import. It will see nothing because it's Swift. So we have to make some changes. The first thing we need to do is inherit from NSObject. Now, NSObject is the root class for all Obj-C classes instead of any, which is what Swift normally uses. And once we do that, the compiler knows that it needs to now build this as Obj-C, and it'll now be visible. And because we're inheriting now from NSObject, we have a bit of extra noise around overriding the initializer and calling super. And the only other thing we need to do is add Obj-C to our method to expose that. And the type in the parameter of the method, the string, that's a Swift type, but it will appear magically in the Obj-C interface as NSString, which is the Obj-C equivalent. And the compiler does this for us. It does this with a bunch of different types, not all types, but if they're compatible, it will do it. And we get this for free, so leverage this in your APIs. If you do put add Obj-C on your code and it's got something in the API that is not compatible, the compiler will flag it and it won't build. So you can fix it right there until you may have to wrap the type in some other structure in order to expose it. Now some more detail on that interop. So use add Obj-C. There's a few variants on that. You can export the entire set of members on your class, or you can export with different names. You have to use compatible types, which means trying to take advantage of toll-free bridging. Only use NSObject. You can't use any other class, superclass. You can't use structs or any of the cool Swift value types. You can't use any generics. You can use some limited set of the lightweight Obj-C generics, but generally no generics. You can't have the default values in your methods. And error handling is kind of awkward. And I'll get into that after we have an example of how to use it. So we're going to build a logger module. So a multi-platform library that just does logging. And we'll spin up this module. We'll have two modules in this project, logs and samples. Samples we'll use just to run and test the code. And logs will be our library where we do logging. And we have every platform covered. So we have a single, very, very simple interface, a single expect function log info that takes a message and it'll log it to the logging system on that platform. Now, on the Apple system, there's this logger thing, this unified logging system that was introduced in iOS 14. And it has a bunch of cool features, and we want to use this. But unfortunately, it's a struct. So we can't call this from our Kotlin code at all. We have to wrap it in an Objective-C API. So let's do that. Let's bring in our same Cocopod structure as before, and add our logger.swift, where we'll write this API in Swift that exposes it as Objective-C. And we need a pod spec. This is exactly like we did earlier, same thing, just different names have changed. And our Objective-C wrapper, we use the same techniques. So we have a public class, it inherits from this object, and we wrap the Swift struct, the logger itself, in a private instance variable. And in our initializer, we'll spin up the instance of that logger. It has certain parameters. We're going to use com.example, and we'll use that to search for our logs later on so we can show it working. And we have two public methods, loginfo and loginfo redacted. Now, the loginfo logs it with public, and loginfo redacted uses the default privacy operators to log that message, which means it'll redact anything that's live data in that string. Now, our Cocoapods plugin, again, identical as before, just .cocoapods. My logger is the Cocopod we're going to bring into our project. And our native code is pretty simple. We import our Cocoapods, my logger that we just built, and we can instantiate the MyLogger class, which is an Objective-C class that hides the underlying Swift member, and then we can call logger.loginfo. And if you're paying attention, you'll notice the method name changed. This is an Objective-C thing, so I guess they think it's too short. They want to make everything longer. So loginfo, that text parameter message is vended as loginfo with message. And if that annoys you, you can override it with a custom name. But generally, I just go with it because that's the convention. So let's demo this. So we're going to build in our samples folder a little tiny app. And we need to spin up, I'm using macOS ARM, so macOS ARM 64 binary. And we want an executable, the entry point is main, and we need to bring in our logs module. So we have the dependency on our logs module inside our project. And our main is pretty straightforward. We'll just print to the console that we're running so we can see it do something. And then we'll call the loginfo function, and that'll call through to that Objective-C wrapper that goes through to the Swift, that goes to the unified logging system on the Apple platform. So let's build that and run it and see what happens. And unfortunately, it breaks really badly. So it didn't even compile. The linker is telling us here that it can't find the MyLogger class. And that's kind of weird because in the IDE it could see it, we could import it, we had autocomplete and everything working, but it doesn't actually work. And this is some known problem that's been around for quite a while, and it might be around for quite a while still. It's definitely being worked on, but it kind of breaks our setup here. So fortunately, someone figured out a way around it. So we can tweak the linker parameters, and in this ticket here, they explain how to do it for iOS tests, because when you're running the tests locally, you're doing exactly essentially the same thing. So we can use the same technique. This is the workaround on our executable configurations for both debug and release. We have an extension function that you could definitely do a better job than this. I just hard-coded the path to the build artifact, and then we add the extra flags we need to link to that, and that'll get us up and running. So now when we build it, it builds, and it should run. It does run, it's successful. And we can scan the logging system to see if our log actually worked. And there's a whole bunch of text there, so I'll break it down. When we executed it, we saw our console log sending message to logger. So it definitely ran, that's good. And there's a command on macOS, log show, and you can give it a predicate to say what to search for. This searches the unified logging system, and we're looking for com.example in the last 5 minutes. We can see there our hello world definitely worked. So that's all good. Everything works great. We can now call Swift, like strictly Swift structs from our Kotlin project, which is super handy because there's a ton of stuff now coming up that we wouldn't otherwise have access to, and we need to use this technique to get to that code. So I'm going to circle back to the error handling that I glossed over earlier. Let's say we had a method with this signature, and we can expose this as at Objective-C, so it appears at Objective-C, but it throws, and that's a Swift keyword. Objective-C doesn't really have throws. This method, we'll assume it does something and does some kind of I/O, and it'll either throw an exception or return the data that we're asking for. Now, in Objective-C, you would write it like this. You would say, I have a method that takes a pointer to a string, and it takes a pointer to an error, and it returns a pointer to the data. And that's the convention in Objective-C. All of the sort of failable functions have this kind of syntax. And if we build this code and then command click on the symbol, we'll see this interface that the compiler generated for us. And we can see it's exactly that. So we have this expect fun, and it's not read file, it's read file with path because Objective-C. And it takes the path, which is just a normal string, and it takes a C pointer to a C object var to a optional NS error, and that whole thing's optional, and returns, it doesn't return data anymore, it returns a nullable data. So it changed the type signature quite a bit, but this is the way errors are handled, and you'll see this a lot if you call any sort of APIs that throw. So we need to be able to deal with this. It's not that hard. Once you do it once or twice, it sort of becomes normal, but it's kind of annoying the first time you have to deal with this. So we have to create the error object itself. So we have to be in memscope, so we have to allocate that. And then we can call the function, and we have to pass it the pointer to the error structure so that the thing it's passing it into can then write back the error if it gets an error. So if it fails, it'll return null instead of the data we wanted, and we can check for that. And then if we do get a null, we'll have a valid error inside that error pointer, and we can access all sorts of properties on the error that tell us what went wrong. And otherwise it worked, and we're all happy. So error handling's kind of finicky, but once you get the hang of it, it's not so bad. It just is the way it is, and we have to deal with it. So what about going the other way? We want to take our Swift code, our Kotlin code, build a library, and then vend that to a Swift project. And we're going to use Swift Package Manager to do this. You don't have to, but it's a really useful set of tools. Swift Package Manager is the replacement for essentially Cocoapods. It obsoletes Cocoapods. It's become the default now system for distributing code in Swift. And it comes with a bunch of tooling that's really handy and gets a lot of things done for us pretty easily. So we have an existing Cocopod structure, and we're just going to wedge in there a package.swift file. And just by doing that, we enable the whole package, the Swift Package Manager ecosystem. And it kind of has a way it wants things structured. You can customize it. I kind of recommend against that because the default way it does it is kind of how everybody does it. It's just simpler to stay in that whole shape of doing things. I've actually got the structure wrong here. There's another layer of directories I forgot to put in there. But I have the source code for this up on GitHub that you can see if you want to see the real structure. So the package.swift, kind of like the pod spec. It tells us what to build and where to get it and that kind of thing. So in this case, we're building a library. So we have a product, which is a library, and the library has a name and a target. And the target is a thing we have to then build. And the target has a name and it has dependencies. In this case, no dependencies, because we just have some local files we're going to build, and we tell it what version to use, and that's it. If we have this package.swift, we can use Swift build and Swift test and Swift run, all of these Swift buildy commands that do stuff. So the code we have in the Cocopod is now also a Swift package, and we can build it for both at the same time. It's compatible with either of them just through these configuration files, the pod spec and the package.swift. In this case, we don't have any tests in there, and we don't have any executables. So the Swift test and Swift run do nothing, but you could add those if you wish to, which means you could write tests for your Swift code in Swift and have them execute using this. The documentation is kind of weird. There's a normal Apple documentation, and there's this GitHub usage document for the Swift command line tool. Definitely check that out. It has a lot of interesting things you can do with these commands. So let's build a small app that does this. I'm not going to use the logger this time. We're going to build a really tiny calculator in in Kotlin as a library. and then we're going to use that from our Swift project. And it's really tiny, it only does one thing. We can multiply by 3. It's not a very useful calculator, but it does do something. And we can expand it later if we wish, but this is what we have right now. And this just goes in our normal common main, and that's all we need. We need nothing else. We have a single file with a single function in it. And to create a Swift project, before we created our package.swift manually, there's a command that does this for you, Swift package init. In this case, we want to make an executable, so we give it -type executable. And when we run this, it does a bunch of stuff. And it builds out the whole of that directory structure and puts in the package.swift file for you, sets up a ton of stuff, and even creates main.swift. So you can kind of get jump-started really easily. Once we have that, we can go in there and edit our Swift code. And Swift package manager folders, if you have a package.swift, Xcode understands it, and it can just load it up. And it'll use it, it can get it from somewhere else and pull it in, it can understand how to pull that Swift code into any Xcode project. Now to build our calculator library to be compatible for Swift, we have to build a fat binary, which is an XC framework. There's regular framework and there's XC framework. XC frameworks can contain multiple binaries for different platforms. In this case, we're just going to build the one, macOS ARM64. And we give our XC framework a name. We're calling it lib, and that's the name of the framework itself. But the thing inside it has its own name, this base name, and we'll call that calc. We just try to make them different. If you make them the same, it gets kind of confusing. Or you can omit, I think you can omit them and just default to nothing. But we'll call it lib and calc. And there's a ton of other things you can do in here. Definitely check out the documentation. Kotlin Native as an Apple framework is a whole section on this. And also there's a bunch of useful things. If you search for XC framework, you'll pull up some pages that have some extra detail on exactly what you can and can't do inside the configuration for these executables. So we have our project, we have our calculator, we have that built. Sorry, we need to now build that. And a task will appear once we add this XC framework configuration to Gradle to assemble libxc framework. And that lib is the name we used. So the name of this target will vary based on what name you gave the framework. And if we run that, it emits a few things that we can see in the build folder. We see these XC frameworks, and there's one for debug and one for release, and this .xc framework now, not .framework that we saw earlier. These can be consumed by any Swift project. And to put in a note that it's kind of weird what we're doing here. We're building this stuff locally, so we're saying we've got this common main with this calculate thing in it. We're building it into an XC framework, and then we also have at the same time a Swift package in this folder that we're going to vend the executable from, and it's going to consume that framework. So it's kind of two steps. We do the assemble libxc framework, and then we can build our Swift code, and we'll pick up that XC framework file and consume it. So our package.swift, we need to do that. And we need to tell it where to get the binary from. And the way we do that is we set up a binary target, and the name lib is that name we use for the XC framework, and then the path to the build framework itself in the build folder. And it's an XC framework. The naming is super important here. There's some strange things happen if you get these wrong. They just fail to work in obscure ways. So the dependency on the executable, that name must match the name in the binary target, of course, but then that binary target name must also match what you compiled in the Gradle configuration. And if you get any of that out of alignment, it will strangely not work, and you won't understand why, and it'll be very obscure. But if you line that all up, it all works great. So let's write our main.swift now that we have our framework building. And we import calc. That's the base name we used on the framework, not the name of the framework, but the name of the thing inside the framework. So we import that. That gives us the module. And then top-level functions inside any module are namespaced with the name of the Kotlin file. So in this case, it was calculate.kt. So that's the name of the namespace that all of those top-level functions live in. Just the way it is. I'm not sure if you can modify that. I haven't seen a way to do it. Maybe there is, but we just roll with that and we use it like this. If you have classes, of course, they namespace within their own thing and you can just use them. So let's try and run this. So we have a Swift project, we've got our library built, and we can run Swift build on our Swift package. And that will build, and it'll use that binary target thing to pick the XC framework out of our build folder and link it in. Then we can run it, and we can see that we ran, and we actually executed that Kotlin code from our pure Swift native project. So that's also cool. That gets us to a point where we can do both things. We can use Swift code from Kotlin and vice versa. And you can do it directly in your project. You don't have to need fancy publishing. If you get scaled up a little bit, you will want to publish things. It just becomes a little bit easier to consume. But for a small project where you just want to test this out or get this in place and figure out how it all works, this is the way to do it. So definitely read the docs. There's a ton of information. The docs are being updated all the time. And there's always new stuff on there. I'm finding out like almost weekly it changes. Be aware of your type mapping. Some weird things can happen. There's a big section in the documents about how the types work. So when you're calling Kotlin from Swift and when you're calling Objective-C from Kotlin, there's two different sets of type tables you need to sort of understand about how things move back and forth. And likewise with errors, throws, and for suspending functions, there's conventions to follow on how to best use those components. I'm not going to go into that today because we don't have time. And definitely use Swift Package Manager because it just gives you a whole bunch of extra tooling that you can take advantage of. And that's all I have. All of the code is on this repository if you want to check it out. And thank you.